the organizer to invite me here, and this beautiful place. And in the first part of the talk, I will give a couple of definitions and some problem related, and then I move to the topic, which is about this hyperelliptic, this abelian variety that are dominated by hyperelliptic Jacobians. So I'd like to give a couple of definitions. So A will be an abelian variety complex abelian variety. Although the definition I give now, you can give for any variety and any field. And I'd like to give two definitions. So definition one is the degree of irrationality, which is a sort of measure. We know that A is not rational, but it's a sort of measure of the irrationality of A. So what is the degree of irrationality so is the minimum of the degree of F when F is a rational map from A to PG dominant. So in the case of the curve, this is just the gonality, but I'd like to, for curve, this is the gonality. But I keep the term, the gonality name for the definition too. In the literature, now it's a little stable after work of Lazarsfeld, but sometimes it's changed the name. So what is the gonality? Of E. I need to keep this. What I call this D of A, sorry. And this I call the gonality of A is the minimum of the gonality of the curve C such that there is a map, just a map from C to A. You can take C smooth. Not constant. So the gonality, so we have clear inequality. The gonality is less than this degree, less or equal, because if you take a line here, general, and you pull back this one, you find a curve of gonality D. And for instance, to say that there is an hyperelliptic curve, the gonality is 2, if and only if there is a map from C to A with C is hyperelliptic. Later we'll ask also that this is dominant in order that the Jacobian of the curve C contains the information of the abelian variety, some information of the abelian variety A. There are other possible definitions that mimic the unirational stuff, for instance, or the irrationally connected, to say that for any 2 points there is a gonal curve and so on, but I don't want to go. Now I give, so the main problem is compute or estimate this and this, this and this. The first, so I give, I collect the two, the result in two theorems. Theorem one is about D of A, and the following. First one, for any A, D of A is bigger or equal than G plus 1. This I given many years ago with Alsati. And then, strange enough, also in the case of the surfaces, the problem is not solved as far as I know. So 2, so G equal 2, and if A has polarization exactly. So for surfaces, the estimate is 3. So when A has a polarization of type 1, 2, irreducible, it means it's equivalent to say that A contains a smooth curve. Well, I don't say nothing about the elliptic case. No, the elliptic case is 2 and the gonality is 2. The genus 1 curve. Curve of genus 3. Then the gonality of the degree of irrationality of A is 3. And this is the only case where we know that there is the equality. For instance, again with G equal to 2 and A a Jacobian, so what we know is that this degree is between 3 and 4. Because we use the Kummer map, is degree 2, and then we project from a singular point. But we don't know for the general one. Because some of them could have also the other polarization, so for general one. So the degree of rationality, and for higher dimension, I don't think that for the generic one, I think I can prove now that this is strict, but but I don't know. Sorry, stop. So in theorem 2, maybe I say something about the proof of this. We borrowed this from the topologist. So we use the exterior algebra of holomorphic form. So call this H of X. This is an homogeneous, is an algebra with a product, which is the wedge product. And they use all the cohomology, but because we are dealing with rational map, we can use only the part which is invariant by rational. So assume that you have a rational map from X to Y. It's possible to prove that the length of this degree of length of X, the holomorphic, the length of this algebra, called this H of X, plus 1 is B divided by D is bigger or equal than or maybe I make a mistake now, the length of the holomorph of y plus 1. Now the length is that you find, the length is the maximum of alpha 1, alpha r homogeneous in h of x such that the product is different from 0. It is the length of, is an algebra which has finite length because of the dimension, and then because you prove that if the length is bigger, pass into the Galois closure, and using group theory and representation of this algebra, there is something that comes from, so you start from A, say to PG, you go to the Galois closure, then you have to group, and by studying this is given by Bernstein and Edmondson, and we copy more or less the proof. They're given for morphisms, for continuous map, branched continuous map, and we copy this. For the second, any question? For the second, for the gonality, we have the following proposition. So if G equal to, then the gonality of A is 2. The gonality is an invariant, is invariant by isogeny, because the gonality is invariant by isogeny. Because if you have a map from C to A, then you take an isogeny to A prime, you have a map from C to A prime. And so any abelian variety is isogenous to a principal polarized one that contains a curve of genus 2. The second one is when G equal to 3, then we know that any abelian threefold is isogenous to a Jacobian, so we have that the gonality of A stay between 2 and 3, and I proved years ago that for very general one, very general abelian variety, abelian threefold, the gonality of A is in fact 3. So there are no hyperelliptic curves. Let me say that to have a hyperelliptic curve, because maybe I forgot at the end. So to have an hyperelliptic curve inside 2A, A hyperelliptic is equivalent by embedding using a Weierstrass point. So you go to the Jacobian using a Weierstrass point, and then you go like this, is equivalent to have a rational curve in the Kummer variety of A. So let me here give a problem of Bogomolov. Also, it is also used for higher genus. He asked if he asked the same question. So the same question. Instead of C for Q bar. So is the general abelian variety of dimension bigger than 3 defined over Q bar contains an hyperelliptic curve or a rational curve in the Kummer. I believe it is very difficult, but maybe now I saw result over Q bar. And then, okay, then also with Alzati again, we proved that if the dimension of A is 4, then the gonality very general. The gonality of A is bigger than 3, and here's 3. And now Claire, I prove there exists a function and K that may be now. I'm not sure if this is correct. Anyway, it's like this. I'm not completely sure about the second part. It should not be like this. Some minus, I'm not sure. Plus or minus. About these constants. Anyway, this 2k minus 1, something like this. Then, if G is bigger or equal, also here I'm not sure if this is bigger or equal, sorry, than nk, then the gonality of A is bigger than k. So yeah, it is important the existence of this function that generalized. Sorry? Otherwise, yeah, you take an hyperelliptic. A very general. Okay. Also, let me mention that, again, Claire gave a new insight on this kind of problem, introducing some very interesting loci. By using the Chow group and the Pontryagin product. So you take the Chow group of A, maybe you tensor by Q, and then you have Pontryagin, because it's an abelian variety, there is a Pontryagin product. And also there is a very interesting idea. You take the ideal I, that are the cycle of degree 0, of dimension 0, and degree 0. Now here you use really that is an abelian variety, so the degree 0, and she defined Vk, the point P in A, such that P minus the origin, Pontryagin product K times this is 0. It is known that by Bloch that this EG plus 1 is 0, but there is a sort of filtration by this loci. And okay. And he proved with a remarkable manipulation, algebraic manipulation, that if you have P1 plus Pk is rationally equivalent, so the same of K of OA, then this Pi belongs to Vk. So in particular, if the gonality of A is 2, again embedding with the Weierstrass point in the origin, you have that the curve up to a translation is contained in V2. So it gives an example when thesis dimension is bigger than 1. And but this is not really like the condition of diagonality. It is more similar to the Weierstrass point. So a point k times this point is a special case of diagonality. And then it is for this that I think then use it to obtain this estimate is not so pleasant. It's pleasant, but sorry, not so. The proposition is that for any A, the dimension of UK is less than 2k minus 1, and 2 if A, the dimension k minus 1, this Vk are countable union of varieties. So it makes sense to take the dimension as the bigger dimension. And if A is very general and K is less than G divided by 2, then, if I don't mind now, Vk, because I have not the right Vk, dimension of Vk is 0. Okay, so it make a generalization of this case. Okay, and okay, now I finished the first part, which is about the gonality and this degree of irrationality, little introduction, and just to is there any question? Yeah, for instance, if you have a Jacobian, then VG, the dimension of, using Weierstrass point, the dimension of VG is bigger or equal than 1. It contains the curve C by embedding Weierstrass point. Okay. So now I will consider not only a fixed abelian variety, but in a family. So let me define, let AG be the moduli of principal polarized abelian variety of genus G, complex. The principal polarization does not play any important role, but it's important that there is one. The principal one does not, of dimension G. So we have this loci. This is the Jacobian locus. The image of the Torelli map. And this is I call this the hyperelliptic locus. This has dimension 2g minus 1, and this one has dimension g plus 1 divided by 2. Okay. Now I would like to define the locus I'm interested, H. A in AG, such that there is a curve C of genus that could be bigger than G, curve, hyperelliptic curve, of genus P that this is such that there is a map from C to A, so the gonality is 2, but we require also that this map is dominant or surjective. So this again, H contains AG, but is bigger. For instance, by using isogeny, so if you think AG as the quotient of AG divided by the SPZ, and you let act an element in SPQ, so an isogeny that maintains the principal polarization, you find the countable number of this component by moving the inverse image of, it is a correspondence given by the isogeny. You find countable number of component in H, and also analytically this show that H is all AG. So it's because the isogeny, all the abelian varieties that are isogeny which one fixed is dense because of the density of SPQ in SPQR. And but moreover, there are other components using prim, for instance, using prim construction. There are many other components. And where P is bigger. So there are many. So the result is the following. Theorem. This is the collaboration with Miranto. First part is that the dimension, we can, again, like in the case of VK, we can define the dimension of H because of countable union. Then the dimension of H is 2G minus 1, which is equal to the dimension of AG. So there are no, so it's an estimate. The dimension depends only on the G, not on the. Second result is more geometric, is consider H intersecting the Jacobian locus, a little more geometric, a little more painful. This contains AG, but if G is bigger than 5, AG is the only component of dimension 2G minus 1 in this intersection. So, for this, yeah, there is an extra work. We need an extra work that we are completing with Beorchi and Zucconi. Naranco, but so now I will explain. But this gives the proof. This gives another proof of the gonality, the result of the gonality, because corollary. If G is bigger or equal than 3, the very general Abelian variety of dimension G has gonality bigger than 2, because the very general one is simple, because a very general is simple. So to be of gonality is equivalent to be dominated by hyperelliptic curve, and then for G bigger than 3, we have that 2G minus 1 is less than the dimension of AG, which is G by G plus 1 divided by 2. So it's like no, this I don't know. We don't know. For the small genus, we can only consider the isogeny. I mean, we can throw away the isogeny, the component that comes in that way. So this does not exist because we can control that. But the other one, by the method, it does not. If I have time, I will explain. Or I will explain. Because it's an infinitesimal method. So for the small genus, does not work. G equal 5 is still in the boundary, but we cannot. Genus 4 is completely out of the control. So let me give the proof, or sketch of the proof. So we start with a basic diagram like this. We take Q inside H, be an open analytical subset. You can change base, I don't think it's necessary, but open analytic subset of a component And then we put in family our construction. So we have a family. So this is contained in AG. This is analytically, so we can find the universal family of A. We can find a family of curves. So this is family of abelian. This is a family of hyperelliptic curve. This is the fiber map. And also, maybe I make some space. So these curves, this is the Jacobian. And obviously, we have for the point P in U, very general. So we have the curve C into A, we call this F, this is the point P, and this is the Jacobian. And also we look at the first order because we want to prove that the dimension of U is less or equal than 2G minus 1. And we assume by contradiction that the dimension of U is bigger or equal than 2G. And so the first order, the differential of this one, give that the tangent, let's call the tangent of P of U just T. So we have a map onto the tangent of AG at the corresponding point that we take like by using but this is also the variation of which structure, but this is an isomorphism, so it's not H1 0 of A. On the other hand, we have a map by the Kodaira-Spencer. This is also the Kodaira-Spencer. The Kodaira-Spencer will go in each one of the tangent of the curve. And let me put here in the invariant. Invariant means that C is in H1 of the tangent invariant, is invariant with respect to the hyperelliptic involution. J star of Y equal to J star. J is the hyperelliptic involution. This is the tangent of the hyperelliptic locus. And here we have the symmetric homomorphism between H10 of the curve to H01 of the curve. And this is, and we look also, we have both maps, but we have this map which is compatible with the story. Then the proof is very simple, very elementary. We take it's a little strange, but so we take now W, let's call W the pullback. So here we have H10 of A. So take W the pullback of H10 of A inside the differential form of the curve, which is an hyperelliptic curve, like this. And take, sometimes maybe I use this as an identification. So take now the Grassmannian G of the two plane of W. And inside G, we take this sigma, this locus, the pencil such that there exists xc non-zero in the tangent of the point P, on the tangent of the point P, I call just T, such that the cup product with view is 0. So it means that we look at two forms that at the first order does not deform the stay of the type 1, 0 in the direction epsilon. So, for instance, if you have a family of abelian surfaces, I thought so, this is just infinitesimal. And now an easy remark is this, that the dimension, if dimension of T is bigger than 2G, then this sigma is all G. This is because you have matrices here, and you have to find a kernel of dimension 2, so it's 2G condition, but there is a symmetry, so 2G minus 1 condition. So there is some 1 that is not, there is some not trivial matrices that vanishes on the two vectors. When, when the dimension of sigma is 2G minus 1, for the second part of the theorem, this sigma contains a divisor. Okay. So let me go to the first part. So when the dimension is bigger than 2G by contradiction, so we can find the general pencil is has some deformation that keep it of type 1, 0. Now we can choose V in G such that the base point of V, so recall that V is inside W, which is the pullback, is inside the holomorphic form on the curve C. So what is the base locus of V? Are the point P of the curve C such that omega of P is equal to 0 for any omega in V. So this is a pencil. So there is a base locus, could be base locus, could not be. And we can assume that B of V is equal to B of W. So we don't increase the base locus of, so you use W to embed, so in Pn, and then you take a general plane that you do not increase the base locus. And now we have a cohomological lemma, an easy exercise, say. And the lemma, we have this cohomological lemma that, we have this lemma that I extract from another old paper, or it's a sort of revival, this, but that I given with Collino years ago. Maybe I give the lemma, then now I may explain. Assume C hyperelliptic, assume C in H1 of the tangent invariant, and assume that V is in the kernel of C, dimension of V, say bigger or equal than 2, the kernel of C is the map from H0 of omega C to H1 of OC, is the K product map, that is the infinitesimal invariant of the Hodge structure. And then C belongs to the kernel of H1 of T, so B base locus, then, and from this it follows, it is an exercise that H0 of omega B, omega minus B, all the ones are in the kernel of this. So not only if the base locus, so it means in that case that the kernel of C contains H0 of omega minus B, that because of this assumption, it contains W. But because it contains W, it means that it contains, well, we can look this, but we can look at this level. This essentially is the preimage of W, goes to 0. But this is injective, because it's in the general point of the your Abelian variety. So this epsilon is 0, and this gives a contradiction with the fact that we've taken epsilon different from 0 in the Grassmannian was defined by this step. So this is an exercise. Maybe I explain where does it come from. Yeah, maybe this could be a proof of this. No, we prove in a different way. No, okay, maybe I can give a proof. I can give a proof of the lemma. I extract the lemma from, well, it is very simple lemma, but let me say what I explain. As soon as you have a family of curves, so you have the Jacobian of this curve, the Jacobian family, and this Jacobian family has a cycle, which is the Ceresa cycle, and which is the curve inside C minus C minus, which is nomologically curved. It's given up to translation, but doesn't matter. So you have from U to the primitive cohomology, maybe 3, you have a normal function. This normal function vanishes on the hyperelliptic locus, and so the infinitesimal Griffiths invariant is 0. And this lemma comes from this lemma comes from is forgetting the normal function and just prove this. But maybe I give the proof of the lemma, or a sketch of the proof of the lemma, which is very simple. So we take this epsilon in H1 of the tangent invariant. This H1 of the tangent we think like x1 of omega 1c over c. I put in the right O is OC. So it's a sequence like this. It's a vector bundle. And the coboundary map of this is the multiplication by this epsilon. So saying that there are two sections that goes to 0, we go back to A. By taking the lifting, so we have the section S1 of S2, V goes to this. We have the left S1 of S2, we lift. We can put this in anti-invariant. We take the wedge of this. The wedge of these are in the determinant of E, which is again, maybe I use too many notation for the same things, omega C. But this becomes invariant, so it's 0. So it means that when we go back, this one becomes 0. And so you prove then that is supported on the base locus. It's exactly like in the proof, yeah, it's something like this. It's the first order in the proof that I gave. So you deform. So you deform the first order your curve. You take the wedge of these two curves. You go in the Kummer. This must go. This must not be deformed because omega 1 by omega 2 is 0. Because in the Kummer you don't see nothing. But the only possibility is that the formation is supported in the branch locus, so that the map deform by moving the branch locus. But if the map moves in the branch locus, then it must have this as the kernel. This was the, so maybe there are other proofs, because this is a simple. This lemma is quite simple. So just to finish, I have 5 minutes, I think, more or less. The second part. So the second part is sigma, which is in the Grassmannian and is the locus of V, such that there is C by V equal to 0. In this case, it could be a divisor. If this is not a divisor, we finish as before. So if this is bigger than a divisor. But what kind of divisor do we have? This is a very special one. Because if the base locus does not increase, we can conclude as before. So it means that this divisor, assume now dimension of U equal to G minus 1. If this is a divisor, is a divisor in W, where the base locus increase. But the only possibility is that what we find, that for any point of the curve, C, we can take not only B, but B plus BW plus some point P. I mean, anyway, I have no time to. So we have just to take the pencil that have more base locus than the original one. So for any point, you can fix a pencil that passes from this point. This is the divisor that we find. So take the section, so this divisor should be, this gamma, should be the pencil V such that for any point P, and in general, the section S1 and S2 of V, so V is contained in H0 of omega minus 3. Something like this. So this is a divisor. Doing in the following way, and following, but now using that, the family of the Abelian variety now are family of curve, not of Abelian variety. So we have part 2 of the proposition. we find one-dimensional family. That is parameterized by the curve C, but in fact up to involution. So by a rational curve, rational, in H1 of the tangent system of D of rank 1. And so before we find that we found a deformation which is 0, we find a contradiction. Now with one less, we find a family parameterized by a rational curve of rank 1. And then the only possibility is that the Clifford by Babbage, well, if they are hyperelliptic, okay. But if these are not hyperelliptic, we find that the Clifford index of the curve D is less or equal than 1, but bigger than 0, because not hyperelliptic. So we have to take care of the hyperelliptic locus and the quintic plane curve. Quintic plane curve is easy, hyperelliptic locus is a little painful. So we have to look at the surface that parameterize the formation of rank 1 and study the one that preserves the trigonality. That is, not all the rank 1 deformation preserves the trigonal locus. So, and it is for this in genus 4 you don't see nothing because all of them are trigonal. So sorry for the little confusion.